right, we are going on to lesson 6.3. 6.3, you are going to find missing side lengths of similar figures. That's your learning target. You are also going to apply scale factors. And you're also going to be able to apply indirect measurement, it's called. You have a lot of things you are going to, concepts you're going to apply today.
Just one day?
Yep, one day. Congruent. You need to know some vocab. Congruent means what? What? Same. Congruent means same. Everything we're talking about today is aligned with congruency, knowing that things are the same. Similar figures. They are the same shape, different size. Same shape, different size. Something you really need to know, they also have congruent, same, they have congruent angle measures. There will be a problem in a homework assignment you will receive soon that is going to be, this is the exact thing you need to know. It's going to say, how do you know that all of a certain kind of shape are all similar? And it's aligned, stop getting sidetracked over there. It's aligned with the fact that they have congruent angle measures. Okay, corresponding sides. The sides of the triangle that are related, I'm going to use the word related or similar to each other. Okay, I'm going to give you a visual. I want you to make a small triangle, and I want you to make a big triangle. They are similar figures. Given that they're similar, it means that they have congruent angle measures. Look how I write congruent angle measures. Ooh, call this triangle A, B, C, and call the big one D, E, F. Okay, so angle A is congruent to which angle?
D.
D. Angle A is congruent to angle D. Angle B is congruent to what? E.
Angle E.
So now we use two lines. You can't use the one because the one is already aligned with A and D. So you have to use the two lines. And angle measure C is congruent to?
F.
How many little lines?
3.
1, 2, 3. 1, 2, 3. Okay, good. Now I'm going to say, I'm going to move this down a little bit. Segment AB is congruent. You call that congruent, equal with a little dash or squiggly line. That's congruent. Segment AB is congruent to what?
Line AB. Or DC.
DC. AB is to the other DE. Okay, segment AB is congruent to segment DE. And segment, I'm going to say BC, is congruent to what?
EF.
EF. Now notice how we write that. BC means I have to start at the top. I start from the top, went to the bottom. Then I have to start at the top. I couldn't call this segment FE. If I start at the top, I need to start at the other top. So BC is to EF. As CA is congruent. Now I'm going to trick you a little bit. What's CA congruent to? Jonathan?
FD.
FD. Now notice what I did. I went from this point over, then I need to go from that end point over to the beginning. Is congruent to FD. So you're going to need to be able to identify congruent sides today. You're going to have to do that. This is a generic proportion setup that you can always use. It should say small side is to the big side as small side is to big side. I'm going to take this out of my lesson though because I think that I don't like it like that. Sometimes you're given the big triangle first and I like to use that. I like to use left triangle is to the right triangle as left is to right. There's so many different ways to use proportions. The biggest thing about proportions and similar figures is they create, their side lengths are proportional. Know that, again, that little squiggly line means similar.
When you put the squiggly line, do you have to put the equal sign?
That means congruent. Squiggly means similar. With the equal sign, it means it's congruent. Okay, so this triangle set here that I gave you, triangle ABC, is similar to triangle FGH. I'm just showing that their side lengths are proportional. For instance, 8 is to what? 8 is to what?
12.
12. 8 is to 12 as, let's do 10. 10 is to what?
15.
Then if they are similar, their cross products are equal to each other. So testing that theory out, just proving that they're similar triangles, you can always prove by setting their cross products equal to each other. 15 times 8 is 120 equals 120, shows that they're proportional. Similar figures have proportional side lengths. Okay? Done. That part done. Now, finding missing side lengths. Would you want to run the bathroom or the nurse? Run to the nurse. Okay. Oh, what happened? Oh, this lesson takes forever. Okay, finding missing side lengths. To find missing side lengths, you set up a proportion in solve. Okay, I like to set it up, the left triangle is to the right triangle as left triangle is to right. That's a good one. Left triangle is to the right triangle as left triangle is to the right triangle. I like to do that. But there's lots of different ways you can do it. So 13, I'm going to say this side length is to what? X. 13 is to X as what?
10 is to 6. 10 is to 6.
That is 100% accurate. You have to go left is to right as left is to right. 13 is to X as 10 is to 6. And then you'll solve. I'm not going to waste your time doing that. Okay, next one. What do you want to start out with?
22.
22 is to what?
4.
As
X is 7.
X is to 7. Now you also, I just want to show you that you could say big side is to big side as small side is to small side. You could do 22 is to X as 4 is to 7. You could do that too. It'll all come up with the same cross product. Notice here, it would be 4X, it would be 4X, it would be equals 7 times 22. Same thing. I just like to do the triangle. Left is to right as left is to right. It's a nice pattern for me. It seems like a lot of students like to write it this way. 22 is to X as 4 is to 7. Either way, it's a strategy that'll work. Okay? Let's see. All right, inner triangles. And you can solve those proportions yourself. I think that you got enough practice solving. You're going to create a proportion with the two triangles and then solve. I'm actually going to get rid of this. Okay. So, the first thing you need to be able to visualize is the two triangles. Can you visualize them?
Yes.
Okay. Let your eyes trace. Where do you think I'm going to trace for the big triangle? Let your eyes see. I'm starting here. See if you were thinking the same thing. That's my big triangle. Do you agree?
Yes.
Okay. So let's think of the dimensions of my big triangle. I have 12. What's the dimensions of the bottom of my big
14.
triangle? 14. A lot of kids think 10. If you are one of the students that thinks it's 10, what helped last hour is when I erased it and I said, okay, they visualized the big triangle, but they're thinking that this 10 is only aligned with the big one. Notice that the 10 stops right there. And is that a triangle? No. I need this dimension plus the other 4 for that total of 14. Okay? All right. And the inner triangle is this cute little guy right here.
Aw.
So cute.
That's so fluffy.
Little bad.
Okay. So I'm just going to start. Big triangle is to little triangle is big triangle is to little triangle. So the big triangle length, you just pick one. I'm choosing to pick 12. 12 is to what?
X.
As
14. 14 is 4.
nice. 14, the big length is to 4. You'd set up the proportion and you'd solve.
What did we have then? Like flip flop, like 12 and 14 on the top.
So you said, what do you mean?
I have 12 as 4 is yeah.
As, oh yeah. So you went small is to big as small is to big. Totally fine. There's lots of different right ways to do it. Okay. You could have also went 12 is to 14 as x is to 4. Shadows, indirect measurements. What we do is draw a picture. It's one of my favorite units. When I have students draw like little doodles, it's so fun for me to see how you guys do. And you create 2 similar triangles. This is a possibility, not the only right answer. It is a possibility. Okay, this first question says a school flagpole casts a shadow that's 8 feet long. So I draw a picture of a flagpole. The shadow is 8 feet long. My friend's shadow, here's my friend, is 5 feet. And my friend is 6 feet tall. So this is actually 2 right triangles is really what's going on there. And I want to know how tall is the flagpole. So I just set it up. 8 is to 5 as x is to 6. And solve the proportion from there. I'm just going to do one scale drawing example. We use scale drawing with maps or models. We use the proportion fake is to real as fake is to real. Here's the first one. A map has a scale factor of 1 inch to 50 miles. The distance between 2 cities on the map is 2.5 inches. How many miles are they apart? So I have fake is to real, while an inch is my fake measurement, is to my real measurement is miles. Okay? 1 is to 50 as, and then I have the distance between 2 cities on a map. Is map fake or real?
Fake.
Fake. A map is going to be 2.5. You could also say inches. Okay, the 2.5 is inches, which is on top. And you know how to solve that. Last one, you're building a muscle for your science fair. The scale factor is 1 centimeter is to 1.5 inches. Your model is 6 centimeters long. How long is the actual muscle? Okay, centimeters is fake, it's my model. So I have centimeters is to inches. So 1 is to 1.5, and then 6 is to x. Okay, fake is to real is fake is to real. That's with scale drawings and models.